Okay, welcome to the class, and we have been discussing this MIMO architecture for FR1 and FR2 band, and whatever we have discussed primarily in context of MIMO is for FR1 band, and we started discussing the MIMO architecture for FR2 band and the need for simplified architectures, okay, for FR2 bands. We discussed that in detail, okay, and the primary reason is that you need many more antennas for FR2 band because the channel is hostile, and then you need them both at base station as well as at the UE side. So we are considering a very simple example, okay, but typically till now FR2 is being used for this single user kind of scenarios and then line of sight systems, okay, where frequency selectivity is not there. It is basically frequency flat channel. Okay, so we discussed one half of it and we'll recap. Okay, so this is the simplified transmitter architecture. So this is the system framework we are considering: single user and frequency flat channel. And so what happens here is, this is hiding, I'll just move it away so that it is. Okay, so this is a precoded vector, okay, V, which is constant across subcarriers, okay, because frequency, the channel is flat across subcarrier and there is only a single user, so the channel is not changing, okay. And this precoding vector, as we know, there are a lot of antennas, and you need these precoding vectors to basically, let's say, do maximum ratio transmission, because it is a single user. What will you do? What is the best thing to do? The maximum ratio transmission, okay, right? And for time being, what we said, there is only one RF chain and one antenna, single antenna. What happens to this V? It becomes a scalar, okay, because now there is only one RF chain and one antenna, okay. So you take some x of k multiplied with some constant V, which is constant across the subcarriers, okay. And to begin with, and this is what we will consider, so V we are writing as some constant phase precoder, phase only precoder, okay. And this is the kind of system we considered for codebook kind of beamforming, wherein you saw that we were feeding only the channel phase information, not the amplitude information, okay. So what happens, this is what we discussed, that if you then when you precode, then what you do after that is basically take the IFFT and then do digital to analog conversion, okay, right. So we write that NFFT, endpoint IFFT operation on these precoded signal just to understand something, okay. So what happens? So this is x tilde k is our precoded signal. It is coming from here. You are using n subcarriers, okay, and this is the endpoint IFFT of the precoded signal. Correct? Okay, right? And now we substitute x tilde of k from here, j theta. Okay, now j theta is not function of k, okay, because it is independent across subcarriers. It is basically constant across subcarriers. Okay. And we can move this out of the summation, and now what is this? This is basically the IFFT of the unprecoded signal. Correct? Okay, e raised to power j theta into what is this? IFFT of the unprecoded signal. Right? So what have we done? Basically moved this precoding from frequency domain to time domain. Right? Okay, correct. And so this is one achievement of whatever we have done till now. Okay, so this is x of n. What we are saying, this is the endpoint IFFT, which is independent of the precoder. When I say independent of the precoder, this precoder is same for all n values. Okay, right? And because we treated that as a constant across time, across frequency. Okay, it turns out that it is becoming constant for time also. Okay, right? So now what happens? What is the kind of system we are considering here? We are considering a frequency flat. Okay, you see the channel is not varying across any of these subcarriers, okay, because it is single user and line of sight system. Okay, so you take IFFT, CP, digital to analog converter, right? Okay, then I'll show you that this operation can be implemented in analog domain. Okay, right? So but here, as of now, it is only for one antenna. We extend this exercise for multiple antennas and then see how easy it is to do this operation in analog domain. Okay. So what have we done while doing this exercise? We have moved the phase only precoding from frequency to time domain. Okay, right? And what have we done? What is the strongest assumption here? Is the frequency flat, and we have allocated entire bandwidth to a single user. Correct? Okay. With that, we are able to basically do this precoding in the time domain instead of doing it in the frequency domain. Okay. Correct. So that's the biggest difference what we are seeing till now. Okay. So, and I claim that phase shifting can equivalently be moved from baseband to RF also. This I have shown that in the last slide, that we have moved from baseband only, baseband frequency domain, to baseband time domain. It can equivalently be done in the RF domain also. Okay. Now what are we saying? Okay. So till here I showed you this exercise for a single RF chain and a single antenna system. Okay. So what am I saying? Okay, now instead of a single antenna, I will consider two antenna system. Okay, RF chain I'll show you, you will still need only one RF chain. Okay, and that's what I'm going to show you. That's how the system will get simplified. Okay, so what are we saying here? That basically, so you have this, you have two antenna system. Okay, right? So from two antenna system, what are you going to transmit? A precoded signal. Okay, x1 tilde of k and x2 tilde of k. Earlier we had only x tilde of k, which was e raised to power j theta into x of k, right? Okay. Now what are we doing? Okay, so this is basically x1 k is e raised to power j theta 1 into x of k, and this is x2 tilde is e raised to power j theta 2 of x of k. Right? Okay, because what are we doing? We are taking x of k. This is happening in the frequency domain, right? Okay, so what are we taking? One symbol, we are precoding it for two antennas. Correct? Okay, so what will happen? E raised to power j theta 1 into xk, e raised to power j theta 2 into xk. This is for first antenna, this is for second antenna. Okay, right? So now what happened after taking IFFT of this system? Okay, so what will you do? So what is this? You have to convert this signal x1 tilde of k, okay, to the time domain. Okay, and what is this? You take n point FFT of that. I am calling this as x1 tilde of n. Okay, right? So what is this? E raised to power j theta 1 x of k, right, into this IFFT operation. Earlier we were considering only for single antenna we had theta. That's the only difference I have done. Okay, this e raised to power j theta 1, and this e raised to power j theta 1 is basically constant across subcarrier. You can move it out. Okay, fine. What happens after that? E raised to power, what is this? This is a time domain signal. X of n into e raised to power j theta 1. Okay, so what? Again, the precoding for first antenna, we are able to move out of the frequency domain to the time domain. Correct? Same thing we can do for the second antenna also. X2 tilde of n. Nothing changes. Okay. Correct? Because what is x2 tilde of k? It is e raised to power j theta 2 into x of k. What is happening? This same symbol is, after precoding, is getting multiplied from the second antenna. Right? Okay. Because that's what we are doing. Okay. We are taking the same symbol, precoding it and transmitting. Okay. So what happens here? X2 tilde of n, you get x2 tilde of k e raised to power, this is the IFFT operation, x2 tilde of k. This moves parallel to this. You will have e raised to power j theta 2. Correct? Instead of e raised to power j theta 1, you will have e raised to power j theta 2 to x of k. Okay, fine. Then e raised to power j theta 2 comes out, and then you have this. What happens? E raised to power j theta 2 into x of n. So similarly for second antenna, this is, the precoding is being done in the time domain. Nothing changes. I moved from one antenna to a two antenna system with the same assumptions that the precoder is constant across the subcarriers. Okay, right? So what are we saying here? Okay, so this is x1 tilde of n, x2 tilde of n are n point FFT of precoded data symbol for two antennas. They are precoded data symbols. Okay, in principle, like we should do this precoding as in the frequency domain. That's what we have been doing. Okay. Now, if this is a special kind of precoder where it is constant across subcarriers, I can do this operation equivalently in time domain. okay, right, x of n, but e raised to power j theta 1 and e raised to power j theta 2. What is it telling us? That you take this, all these symbols, OFDM symbol, take all these subcarriers, okay, take IFFT, then do the precoding, okay, right. So what is happening here? Now you have two antenna system. What are we doing? Okay, right. You remember if we had 64 antenna system, how many point IFFT you had to do? 64 different IFFT, because you are creating 64 different resource grids, right? Okay. What are you doing here? You are creating only one resource grid, right? Okay, and digital to analog conversion, up conversion, and then do this phase shifting in the RF domain. Okay. So what is happening? You have only one RF chain. And how many antennas? As many antennas as you can want to have it. Okay. There is no restriction on the number of antennas, because number of antennas when compared with RF transceiver, okay, is a very small piece of hardware. Okay. Right. Here you know for each chain you require two digital to analog converter, one up converter, one power amplifier. Right. Okay. So this is how we are reducing it. So you look at this. This is the architecture I was alluding to. Okay, right? How many? There's only one pair of DAC, one up converter. What are these? What have we done? Okay, right? You take get the IFFT of one corresponding to x of n. Okay, do the up conversion. What is this? E raised to power j theta 1, e raised to power j theta 2, e raised to power goes on, e raised to power j theta, whatever antennas you want to have. So what have we done? By making some certain assumptions on the system, okay, we have been able to move this precoding from the frequency domain to the time domain. And how is it helping? It is helping us in reducing the hardware immensely. Okay, equivalent. You are able to equivalently do it in the time domain with only phase shifters, antenna and phase shifters. Okay, so this is basically called the analog transmitter architecture. Okay, whatever we studied earlier was completely digital. Okay, and this part of the precoding was done completely before this, right? Okay, and what did you need to enable that? You need as many RF chains as the number of antennas. Okay, right? So this is simple analog transmitter architecture with one RF chain and multiple antennas. Okay, and you will get all the precoding in, because as we remember, like when for the code book based beamforming, what was happening? We were basically doing this phase only feedback, and I claimed that we'll be getting most of the gain, right? Okay, that's what is happening. Okay, so this is the transmitter architecture used in 5G NR for FR2. This is one kind of architecture. Don't generalize it, but typically this is most commonly used. Okay, right? And then what are we saying? Be careful about where this architecture is applicable for single user flat fading channels. Okay? Basically line of sight, right? Okay, you have to ensure that channel doesn't change across subcarriers. Okay, and you have to satisfy these two conditions. Now what happens? This is a receiver architecture. Do the same thing at the receiver also. The receiver has multiple antennas. As I told you in the beginning of this class, that receiver also needs to have not 2, 4, multiple antennas, so that it can combat the hostile channel, FR2 hostile channel. Okay, so this fellow will also do the receiver same operation will happen. Okay, right, because receive combining can also happen in a similar way. Whatever way we did the transmit combining, receiver combining will also happen in a similar way. How will it happen? You will have these multiple antennas, band pass filters, then you will have phase shifters, combine all of them, then do the down conversion, ADC, you get a single, basically a single symbol x of n, right? Okay, all that precoding has already been done in the analog domain, correct? Okay, so it doesn't matter, right? What are we achieving with that by doing this? That you want to precode, correct? But you want simpler architectures, you are able to do that. Okay? This precoding is very simple phase shifters. Okay, now right? So one RF chain and multiple antennas. Whatever precoding gain you are getting at the transmitter side, the similar precoding gain you will get at the receiver side as well. So now what happens? So this is one, okay, correct? What is happening? So what are we moving from? MIMO transmitter architecture in 5G NR with two RF chains, okay? So whatever I showed you earlier was completely analog, okay? Now what are we saying here? This is something typically known as hybrid, okay? So what are we doing here? This is happening for one, let's say, user, right? Okay, correct? So this is, we discussed, okay? What happens here? Now you consider one user which is basically oriented in this direction, which is located here, okay, correct? Then you consider another user which is located in this direction, okay. Now, so there is one user, there is another user here, right, okay, correct. So of course had multiple antennas. Now what was the limitation earlier, okay, that we could serve only one user in entire 400 megahertz band, right, okay. So if I do this kind of architecture, I serve one user with the pencil beam here, right, another user with the pencil beam here, correct. What are we doing? Basically serving more than one user on the same 400 megahertz band, right, okay. But for each one of them I am generating the signal such that they don't interfere with each other, right, okay. What is this? These are considered, you are transmitting two layers. What will happen at the, what will MAC layer do? MAC layer will give one transport block for one layer, for one user, another transport block for another user, okay. For each one of them you are doing this analog beamforming, okay, but you are doing them simultaneously on the same 400 megahertz grid, right. So this is an example of extending that single user architecture, analog architecture, to multi-user analog architecture, okay, right. This again, there is one flavor of it, right, okay. So there are multiple such architectures. So you can call this loosely as a hybrid architecture, okay, wherein you are able to basically multiplex more than one user. You have another system like this, you put another system like this, okay, there is another user basically which is located far away from these two users, you can multiplex that user also, okay. What are we doing? We are saying, we are figuring out those users which have kind of like well separated channels, okay, right. Their channels, if you see, they kind of orthogonal to each other, okay, right. So they don't interfere with each other. I can serve both of them simultaneously on 400 megahertz band also, okay, by using this kind of architecture, okay. So the base station will have multiple such RF chains, 1, 2, 3, 4 maximum, that's all, but each one of them will have 64 to 128 antennas, okay. This is not, so what is this? This is not digital architecture. For each one of them we are doing analog beamforming. This is for user 1, this is for user 2, okay, right. So simple analog transmitter architecture with two RF chains and multiple antennas, okay, correct. And then what happens? This is receiver architecture, counterpart of that, okay, wherein like this is one user, this is another user, okay, correct. Or you could have on the same user also, if you can, they are well separated, like one, you can basically, you can have a laptop kind of a system, right, wherein one patch antenna you put on one side, other patch antenna you put on another side, okay, but not in a typical normal mobile system, but if the, like your device has a like large dimension, okay, then you could do this also, okay, right. So that's how we are basically extending this simple analog architecture to something called hybrid architecture, okay, fine, with two RF chains and multiple antennas, okay. So now this is one way of serving multiple users, okay, right. Now let's say you don't consider this, you come back to our like one RF chain and multiple antennas, okay. How do you serve multiple users there? Because each user you are allocating the complete 400 megahertz bandwidth, okay, right. So I'll show you, it is inherently there in the slot structure itself, okay. You'll see that like immediately kind of the subcarrier separation we use in millimeter wave FR2 systems, you will be able to serve multiple users much better. Multiple users also like in an architecture like this. Okay, let's see that. Okay, so what happens? So how do you serve? Okay, that one way which I showed, you will have to keep extending the number of RF chains, right? What is the other way? Okay, so if you go back to the slot structure, what happens? Remember this, right? Okay, what is this? One frame, 10 millisecond, okay, right? Then what happens if the subcarrier spacing, which is typical FR1 spacing, this is 30 kilohertz, slot duration is 0.5 millisecond. This one slot, okay, you can basically, what happens, you can, let's say you give one symbol to each user, right? Because what is the constraint in this FR2 architecture we are considering? You have to give entire 400 megahertz band to each user in each symbol, right? In the next symbol, I can basically serve another user, right? Because the next symbol is another resource in a slot, okay? So first symbol is allocated to first symbol because then the precoder will remain constant across all the subcarriers. Second symbol, I give it to another user, right? Okay, fine. So if you look at a slot, basically, how many users can I serve with the architecture I have? One RF chain and multiple antenna. I can serve 14 users in a slot, right? Okay, fine. And that 14 users in a slot basically over a duration of 0.5 millisecond if it is a 30 kilohertz system, but that's not the case. Okay, what happens if it is a millimeter wave system? Okay, FR2 system. If this, then I said typically the subcarrier spacing is 120 kilohertz. Okay, what is happening? This the kind of like the relationship between the subcarrier spacing and the slot duration. Okay, they'll again help you in serving multiple users in very small duration of time. How? Because if you look at from 30 kilohertz to 120 kilohertz, okay, the slot duration is 0.5 millisecond. Here, the slot duration will become 1/4 of that. Right? Okay, so 0.125 millisecond. Okay. Again 14 symbols, correct? Okay, so in each of the symbol, you basically serve one user, right? Okay, the slot duration has come down considerably, right? So that will allow you to multiplex user faster by giving each user complete 400 megahertz, right? And by doing phase only precoding in analog domain, there is only one RF for each user. You will need to have one RF chain and as many antennas as you want, okay? Plus the delay of serving each user comes down considerably because the slot duration is smaller. Because the subcarrier spacing has increased, that reduces the slot duration and then in turn help you in serving the users fast, correct? Okay, so this is what I said here. Slot duration for FR1 system with 30 kilohertz subcarrier spacing is 0.5 millisecond, okay? Right, slot duration with 120 kilohertz is 0.125 millisecond, okay? Multiple users are served using shorter slots or shorter symbols, okay? Right, in the same duration, if I'm, and just for example, allocate a complete slot to a user also, okay? When compared with this system, I will be able to serve in the same duration, I will be able to serve 4 times the number of users, if I'm, right? Okay, correct. So this is because this duration has come down. Okay, right. So this is basically the FR2 system. Okay, a simplified architecture, and I have to like alert you also. Okay, the kind of architecture we have considered. I've given you a very simple example. Okay, right. People have much more sophisticated systems also. Just to give you an example, let's go back now that we have understood this. Okay, this has one RF chain, let's say 64 antennas. Okay, right, so one RF chain is connected to 64 antennas. Why not connect this RF chain to these antennas also? Right? Okay, why not connect this RF chain to these antennas also? Why do we have this kind of block structure? This is simple to implement and simple to like basically design to extend it from one RF chain to 2 RF chains. Okay, but then if you look at a millimeter wave literature, you will find all sorts of transceiver architectures. Okay, this is one of that, and what people do is connect this RF chain to these antennas also, these phase shifters also. Okay, right, so that you could do, because you look at this, when you connect these antennas, this RF chain is connected to these antennas, this RF chain is connected to these antennas. You can do something called digital precoding along with this, what you call as analog precoding, okay, right? So that there are, okay, so just don't get carried away by this fact that there is only this architecture for FR2 system which exists in the literature. No, there are this is one, there is this one connecting RF chain to all the antennas, that also exists, okay, that gives you better performance than this, because again you are complicating, okay, right? So the precoded design will be slightly different, okay. So now this actually brings us to a closure of this, like the MIMO architecture, understanding MIMO architecture for FR1 and FR2, okay. Our primary requirement was for FR2 system that it should be much more simpler, because now what is happening, there like you don't have to really transmit multiple layers in parallel, okay, wherein there is entirely like 400 megahertz huge bandwidth, okay. You can serve the data rate of each user without doing this fancy multiple layer transmission, okay. And then in the beginning, the kind of systems, millimeter wave system, they are like designed for line of sight, okay. So these two requirements have helped us in simplifying the transceiver architecture. Plus this also helps in the fact that for a millimeter wave system, user also needs to have multiple antennas, okay, right. As we discussed last time, that for a millimeter wave system, the antenna spaces reduces, okay. You can have 256 antenna in a patch of this size, but you cannot have 256 RF chains, okay. It's not only about the space constraint, plus the power consumed by each of the RF chain is humongous, okay. Your battery will run out in no time, okay. This kind of architecture, very simple, one RF chain, right, and all these are like they consume minimal power. Phase shifters and these antennas, they consume minimal power, okay. That's a key point behind implementation of these MIMO architecture, at least on the user side, okay. So I'll stop here. Then the last two classes, I'll basically talk about the initial access, which we have not spoken. I'll briefly be able to tell you for the time we have, okay. Thank you.